also started recording for this lecture. Okay. So I hope all of you can see the screen. So we had started chapter 3. In last lecture we covered single sideband amplitude modulated signals. We also did this example. So today we will start from this section, demodulation. How to get back the original signal from single sideband amplitude modulated signals. So first of all, we would need a synchronous demodulator, the same demodulator that we saw in double sideband suppressed carrier. Because remember, at present in our single sideband, we have not sent any carrier. It is not like conventional AM where you have a very large carrier, and at the same time we have still not added any pilot as was added in double sideband suppressed carrier. So at this point of time, we are just sending and receiving this SSB signal, and we will require a synchronous or a phase coherent demodulator. So let us assume that the signal that was sent was a single sideband, but this single sideband was the upper sideband. Single sideband signal was sent as an equation we saw earlier, that this negative sign will give us the upper sideband, positive will give us the lower sideband. So we assume that this upper has been sent. So this upper is the received signal. It will be multiplied by our carrier at the receiver. All right. So this could be a local oscillator that will be generating this cosine of the same frequency as the frequency that is present in the received signal. If it is not synchronized, then there will be some phi phase shift between this carrier, which is locally generated at the receiver, and the carrier which is inherent in the received signal. So our received signal is just U of t, the upper signal, multiplied with this local generated cosine wave. All right, with if there is no coherence or it is not phase coherent, there will be some phase shift. So some of the steps are missing here. So I have done all of this notes. What happens? You have an upper signal. U of t is the received signal, so we are sending a upper sideband. It is multiplied with a locally generated cosine. So this is your upper with minus. This is Hilbert sine to sine, as we discussed in the last lecture, multiplied with this locally generated cosine. So multiplication will give a cosine with both the terms. I can apply sum angle, because this is product. This can be written as sum of two cosines divided by 2, alpha plus beta, alpha minus beta. And similarly here, you can write a sine and a cosine as sum of two sines. Here, this will be cos of minus phi, but we know cos of minus phi is equal to cos of phi. So Now we have this signal. This signal will be passed through a low pass filter. At the receiver, you will always have a low pass filter. When you will pass it through a low pass filter, all the terms which have the high frequency carrier, they will be neglected, and you will get this cos phi and sin phi at the output. So this will be your signal. You can very well see also here. Sorry for this interruption. All right. So you will get this signal. All right. Just pass it through a low pass filter. So you will be getting this signal as I have just shown you. So you will get this signal as shown here. So I think there is one mistake here. This is m hat of t, which means Hilbert of t, Hilbert of m. So by mistake, this was not written here. This will also be m hat of t or Hilbert of m of t as given in the book. Now here you can again very well see that this phi reduces the amplitude of the desired signal, and it also results in the presence of the Hilbert or the m hat of t signal, and hence you can see the overall signal is affected. But if we send a carrier and we have a phase coherent, a synchronous demodulator, which means that our receiver will generate a carrier which will have phi 0 because it will be exactly in phase with respect to the received signal. In that case, once phi is 0, you can see sine of 0, this will be totally 0, this will be neglected, and cos of 0 is 1, and hence you will be able to demodulate the exact signal. But when we get this phase coherent reference signal, one thing is that you send a pilot signal. So pilot signal is a signal of the same frequency as of the carrier frequency of your AM signal, but its power is small. That is why it's called a pilot tone. But still, even if it is of small power, you still have to allocate some of your power uh, to this pilot carrier or this pilot tone. And you can see the advantage of SSB signal, that you are just sending a single band, maybe the upper or the lower, but instead of requiring 2W bandwidth as you were requiring in double sideband suppressed carrier or conventional AM, here you just require W bandwidth. So very attractive for voice communication over telephone channels, because you will require half the bandwidth, and a pilot tone will be always sent for every user, so it will help us in synchronous demodulation. Another method for demodulation is the filter method. And you can use this here. I think it's also shown previously, this one, that you multiply, but then you pass through a band pass filter so that you get only the upper or the lower sideband. And but again, we saw the drawback that you need to have a very extremely sharp cutoff in the vicinity of the carrier to reject the second sideband, but that is difficult to implement. Now we come to the vestigial sideband AM. Now we know in single sideband, as we just saw earlier, that you have very strict requirements, stringent requirements of the sideband filter. But in vestigial sideband, you can apply a vestige or a portion of the unwanted sideband. So you will have the upper or the lower sideband, but along with the upper, you will have a portion of the lower, or along with the lower sideband, you will have a small portion of the upper sideband. So bandwidth is increased but modestly, and this is called vestigial sideband amplitude modulation. This is actually done especially for video signals which have strong low frequency content. And this is used in standard TV broadcast, so that you do not require these sharp filters, as well as you are able to send the low frequency components without any cutoff. From let us say if it is upper sideband signal, you will be sending the upper sideband along with a smaller or a small portion of the LSB or the lower sideband. Now, how can we generate this vestigial sideband AM signals? So again, we first of all generate a double sideband suppressed carrier signal, and then we pass it through a sideband filter with the frequency response HFF. So you generate the signal, but you pass it through a filter with a response HFF, figure 3.17. And time domain, this will correspond to our double sideband signal being convolved with the impulse response of our filter. And frequency domain, we know this is modulated signal at plus FC and minus FC. Frequency spectrum has shifted to plus and minus FC, and convolution is multiplication. It is just being multiplied with HFF. This is my vestigial sideband signal. So question arises, what should be our HFF? So in order to answer this question, we have to see how we will be able to demodulate our vestigial sideband signal. So demodulation is again the same. You multiply this with a local oscillator at the receiver, and then you pass it through a low pass filter, as we have seen many times. So the product signal will be equal to U of t, which is the received vestigial sideband signal, multiplied with the local oscillator at the receiver. Again, you know, this is modulation, hence U of t spectrum will be shifted by minus FC and plus FC. So some of the steps are missing in order to arrive at this equation. So we will shift to our notes. So we have seen that actually our vestigial sideband signal's frequency response is as follows. It is the shifted version of the baseband signal at FCFC multiplied with a specially designed filter, or this was the time domain expression of this frequency domain expression. At the demodulator, we saw that this u of t is again passed or multiplied with a local generator, cosine generator. So your frequency response of this v of t, which is the output of the product of the vestigial sideband signal with the local oscillator, will be u of f minus fc, u of f plus fc over 2, 1 over 2 because of this cos. Will be our u of f minus fc. Now, this can be easily found because we know u of f is this. So u of f minus fc, will be minus 2fc, and this will be f, and this will be f minus fc. So same thing is written here. Again minus fc, again minus fc, again minus fc. But this fc cancels, this becomes m of f, hf minus fc, this becomes m of f minus 2fc. Similarly, what will be our u of f plus fc? So in all the terms, you will just add plus fc, plus fc, plus 2fc. This will be f plus fc, f plus fc, and this becomes m of f. So you can see in both the products, you have a low frequency part, and then you have a high frequency shift of your baseband signal. Now I add both these terms, or I put the values of these two terms in this equation to get the output of the product of the vestigial signal with the local generator. So you will be getting this term. Because each of these terms will be divided by 2, this will become over 4. These two terms are for the first term, and these two terms are coming from the second term, from this one. U of f plus fc, this is coming from u of f minus fc. Now I will pass it through a low pass filter. So you can see this and this, they will be deleted or neglected because these are high frequencies. You will just get this and this. So you can take mf common, and inside you will get this term. So our requirement that the received signal v of f is equal to m of f requires that this factor must be a constant in the range for which your vestigial sideband signal is exist. You would need this to be a constant so that you can get back your m of f. So now we can this is what is required, that this terms needs to be a constant. Now it is explaining to that what could be this type of vector, this type of filter. This filter is appropriate HFF because once you shift HFF by minus FC, so the whole of this spectrum will be shifted towards the right, or you advance HFF by plus FC, whole of this spectrum will shift towards the left. So these two are shifts or values of HF plus FC, while this and this are the values of HF minus FC. Here you can see the combination or addition of this and this can turn out to be a constant provided the rate of increase of this and the rate of decrease of this are at a constant rate, so that their combined effect will give you still a straight line from minus W to plus W. This is the main objective of our HFF filter. So this filter, this was giving us the upper sideband, this was the upper side, but also a small portion of the lower sideband below FC. So you can also have another filter which is actually giving you FC. It is giving you the lower sideband, but also a small portion of the upper sideband. That will also be called a VSB filter. So VC is FC is the carrier, and we just take a small vestige. In this case, we have this lower sideband, but we will take the small vestige of the upper sideband. So we just take a very small vestige of the upper sideband, governed by the frequency FC plus FA, or in other words, FA. But you know, this FA is much less than W, a small portion, that you are just sending a very small portion of the lower sideband, which is whose the lower or upper sideband, whose actual width was W, but you are just sending frequencies up till FA. So most of the time we also have some linear phase over this range from FC plus W to FC minus FA. This is the other side, the lower or the upper, and this is also giving you the complete lower and upper. So the phase is kept to be constant. Now let us go to this example, and we want to find the filter that passes the upper sideband of this signal once it will be modulated, but also the first frequency component of the lower sideband of this signal once it is, you know, modulated by the carrier. Here there are some mistakes here in this expression, but this explanation is accurate. Again, some mistake in the figure, so I will be again referring to my notes so that you can also understand what is wrong in some of the steps in the book. This was my explanation that your HFF would be increasing around FC from FC minus A to FC plus A. Then you will have other filter response will be coming here. So both of them will add to give you a constant height. Now, this is the same example as shown in the book, but here I've done all the steps. First of all, M of t is this. So I write its Fourier transform M of f. And you know each cos will give me 2 impulses in frequency. So you will have actually 2, 4, 6 plus 1. So you have actually 7 different impulse responses at different frequencies. We know that our double sideband suppressed carrier signal will be multiplied. This M of f will be translated or advanced, or in other words, M of t is multiplied by cosine. So I need to know MF minus FC and MF plus FC. So I find my MF minus FC. Just divide all the, substitute each F by F minus FC. F minus FC. So again, you will get those 7 terms. Then I will find MF plus FC. Again, I will get 7 terms where each frequency is shifted from F to F plus FC. Again, 7 terms, 7 terms. So when I will be adding these 2 terms and dividing by 2 to get the frequency spectrum of my suppressed carrier AM signal, I will be getting actually 14 different impulses. This will be the answer. 4 here, 4, 4, 12, and plus 2, 14. and the book was actually showing 2, 4, 6 and 2, 8 impulses. So it is not right. Actually, you will be having 14 different impulses, but these impulses, they represent both the upper and the lower sideband. Now we design a filter so that we pass the upper sideband completely, but only the first frequency of the lower sideband. So what we want here, you can see here, this frequency is at, f shifted to fc plus f2. So frequency greater than fc. This is your upper sideband. This needs to be passed. Similarly, this is also, you can very well see, upper sideband in negative frequency. This will also be passed. Similarly, this is upper at fc plus 10. This will also be passed, and this is also upper at negative fc negative 10. This will also be passed. So these four will be passed by our filter. This is the carrier, standing at the carrier. So this also will be passed, and these two are again at fc plus 1. At also, this is frequency greater than fc. This is also upper. So this and this will also be passed. Now these two will also be passed, and they will still be passed when they are still lying in the lower sideband, because we have to pass the frequency of the lower first frequency of the lower sideband. All right. So these two, sorry for the mistake, these two frequencies, they are the upper sideband. This is lying at minus common fc plus. This is upper sideband signal. This is upper sideband signal at the negative frequency. These two are to be passed, but these two which are in the lower sideband, okay, they are still being passed. This is fc minus 1. If I take minus common, fc minus 1, this is a lower sideband signal, and if I take minus common, this will be minus fc plus 1. So this is also the the frequency, the negative frequency impulse. So these will also be passed. So I will need a filter that will pass these two, these four terms, and these four terms, and these four terms will be neglected. You can see these constants. So once you will be adding the above two equations with these factors and then dividing by 2, you will be getting the answers there. 10 plus 10, 10, 10. Two different impulses, 10, 10 divided by 2, you will be getting 5. There is a 5 here, and the rest of the terms can also be driven very easily. So what should be my filter response? So the book gives a hint here with some mistakes. So fc is the carrier. So I need to pass the complete upper sideband, but I also pass first frequency of the lower sideband, which is actually at fc minus 1. And then I also need to have this slopey structure, because finally what is the condition that this thing, its fc will shift here, and once this fc this will be advanced, delayed, this will come here, and both their additions will give us a constant height. So I choose a slope alpha for this line. So fc is here. This is fc minus 1 plus fc, or frequency will be actually fc plus 1, and this frequency will be fc minus 1, which is being passed. So this could be my half minus alpha. This height could be, half plus alpha. And FC will be at half height, half, and then half plus alpha. This point will lie at half minus alpha. So that is what I have also shown here, that FC I place at half. So FC plus 1 I place at half plus alpha, because I am shifting from here to here in one value along the x-axis. So I will shift, which is alpha. So the value will shift from half plus alpha. Similarly, the value can go from half minus alpha. Again over a shift of 1. You can find also the slope here, and you will see the slope will come out to be alpha. Alright, this is one way. You can use different values of alpha or different ranges of frequencies, but the main point will be that you will need to satisfy the frequency response as required in the question. So we will have unity gain for the range f of fc less than or equal to 2 or equal to 10. Because of this above arrangement. So we can assume, let us say that we have a gain of half at fc, which I was telling you. At fc you have half gain. So fc plus 1 you have fc plus 1, and fc minus 1 you have half minus alpha. Where alpha, it's some parameter between 0 and half. This is also the spectrum which is shown here. But this is not half, this is actually half minus alpha. This point alpha is half, and this will be half plus alpha. So I hope all of you have understood the VSB, vestigial sideband AM filter. Now we go to the implementation of AM modulators and demodulators. Now remember here in AM, you are shifting the frequency of the signal from a low pass to a band pass signal. This means you are generating new frequency components, and this means that the modulators are in general non-linear, because you are shifting them to new frequencies. So there are various techniques to perform this modulation. One is use of a PN diode, and we know its voltage current characteristics are as follows. So the signal that comes in the diode or in this device with this response is a message signal plus the carrier. So the output of the diode will contain many terms, and we will then pass these terms or additional terms or all these many terms through a band pass filter, which will just take those terms which are around FC. So you can see the opposite will be happening in case of a demodulator. In demodulator, we are putting a low pass filter, but in case of a modulator, to make an AM signal, we are putting a band pass filter after our non-linear device. For example, let us say this is the output response of my PN junction or PN diode. So I will add the baseband with the carrier, or the modulating signal with the carrier to get the modulated, to give the sum of the signal. This will pass through a nonlinear device. It will give me many terms, and will just take those terms which are around Fc. So my input signal will be the sum of message plus carrier, and the output will be A1 into this input plus A2 into this input square. So you can see you will be getting these two terms, and then 3 terms will come from A plus B whole square term. So this comes from the square terms, also the square term, and you will have one term mf1 of t, but this term will have a carrier at Fc, as well as the other term 2ab will also have a frequency at Fc. So its term 2ab comes here, and this term comes here, and these two terms are at Fc. Remember that this term will be 1 plus 4Fc, and again it will be at 4F, while this term will be at Fc, while this term will be at 2Fc. So I will pass it through a filter at F6 Fc. All of these three terms will be neglected. I will just get this term. Here we make sure that A1 or this term is much less, or A1 is greater than 2, A2, and hence we are dead sure that this signal will be the famous conventional AM signal used in radio broadcast. Next example is of a switching modulator. You can also generate an AM signals by the help of a switching modulator, and the system is shown in figure 3.24. Sum passes through a nonlinear device, and the output is taken output from the load register. This is the characteristics of the circuit. Sum of the message and carry will be again MT plus AC cos, that will go into the diode. Here we make sure that AC is much greater than MT. So you have just placed a resistor after the diode, so the output of the diode will always exist when the sum signal is greater than 0, but once it is less than 0, it will be 0 because of the switching modulator will be getting 0 once it is less than 0. So we can also view the output as sum of the input signal multiplied with the switching function. So this is the switching function. So it is 1 whenever the input is greater than 1. You will be getting a 1 here. so I can make its Fourier series. This has been also done in the chapter 2. You will just multiply this S of t with your sum signal. So you just multiply sum signal of the low pass and carrier with this switching, and get all these terms. This will go with this term, giving you, 2n minus 1. So if I take n is equal to 1, this will be 2 minus 1, this will be 1. So this will be again your signal at the carrier. And this term also go with this. This will also be the term at the carrier. Other terms you can very well see that all the other terms will be at higher frequencies. All right. Only this term with this will be at FC, or this term with this will be at FC. So if I pass it through a band pass filter tuned at FC, I will get only these two terms. Rest of the terms will be neglected. So you will be getting, because AC is much greater than 4, hence you will be getting a conventional AM signal once you pass this V03T through a band pass filter. Another thing that you can use is a balance modulator. And balance modulator is actually two conventional AM modulators arranged like this. So you have two modulators. One is doing with MT and the other is doing with minus MT. And once you will add them, you can see that this, if you basically subtract them, then this AC term will cancel and the other terms will be, plus minus minus plus 2AC times cos. Hence, this is a double sideband suppressed carrier signal as compared to this signal and this signal. So we have to take care that both the modulators have the identical characteristics. So the signals that they generate are identical with only a negative sign change, and once you add them, you get back the double sideband suppressed signal. Then we have the ring modulator, and it is shown here 3.26. So the diodes, they are controlled by a square wave of frequency Fc. So in the ring modulator, this square wave carrier is working at Fc frequency that will govern the switching. Once Ct is greater than 0, so this is positive, negative, this is positive. So this diode and these two this and this diode, they will conduct, while these two diodes, they will not conduct, because uh, they are more positive with respect to this side, hence they will not, these cross arm diodes, they will not conduct, only the upper and the lower they will conduct. So it again means that we are multiplying once these two are conducting. So in effect we are multiplying m of t when your signals are going in this direction, and once this is positive, this is negative, then you can very well see that these cross arms diodes, they will be basically conducting, and in that case your direction will be exactly opposite. So you can say that as your CT alternates with positive and negative polarity, the output signal is multiplied with opposite directions with +1 and -1s. This CT can also be represented by the same signal with just a constant change as in the previous case of a switching modulator. You can again multiply this m of t with this CT, and you will then pass it through a band pass filter. So you will get only those two terms which are at FC frequency, while all other will be rejected, and hence you will get a double sideband suppressed carry. So we can say that this balanced modulator or ring modulator, they actually multiply the signal. They actually do addition and then pass through a non-linear and then a band pass filter. But we can, the first overall output means you are multiplying the signal with the carrier. So we also call this the mixing operation, and we call the balance modulator also as a mixer. In single sideband, we need to have empty, then one empty goes to a Hilbert transform, it becomes m hat of t, then one empty goes with a sine, other empty goes with a cosine. So you will require two mixers because you need two multiplications. But if you use the other approach where you have a single sideband and then you pass it through a filter which just gets the upper sideband, so in that case you will just need one mixer or balance modulator, because you will just multiply your input signal, it will become a double sideband, and then you will pass it through a frequency or through a filter which gives you the upper or the lower sideband. You just require a single modulator. Now we will discuss how can you detect your received modulated signal to get back your baseband signal at the receiver. The most common use is of an envelope detector. So the circuit diagram is shown. It is basically a diode and then an RC circuit, where RC is a low pass circuit. So it overall acts as a low pass circuit. So remember, in modulator you were having a multiplier, and then you were basically passing through a band pass. But here you are passing through a diode and then you are passing through a low pass. There was also a nonlinear device. Here is also a nonlinear device. But here you have a low pass circuit. There you had a band pass filter. This is your very simple envelope detector. So what happens in the positive cycle, this will be conducting, capacitor will be charging, but once the input voltage drops below the capacitor voltage, then the diode will not conduct. There will be no more charging of the capacitor. Capacitor will start to discharge across the resistor. As it discharges, once its voltage becomes less than the incoming voltage, again will start to get charge. So this charging and discharging will go on and on. First charging, discharging, charging, discharging, will continue going on. Now we will select the values of RC so that our especially discharging follows the envelope as much as possible. Okay. We do not want RC to be too much small, all right, or the time constant to be too much small. And in that case, this thing will happen that yes, you are sorry, this thing will happen that you are charging from here to here, but as soon as your voltage becomes greater than the input voltage, you start discharging. Then again you are charging. So your signal will look like this, and it will not follow the envelope of the AM signal which it need to follow. Other case is that you have very large RC or your time constant is very large. In this case, the capacitor will actually charge and discharge too slowly, or discharge. The problem is always the discharge. Discharge will be too slow, and again it will not follow the envelope. So you are discharging very slowly, and the envelope is here, but your output signal looks as follows. So we need to have a term of RC, a time constant, which is in between the time given by 1 over Fc and 1 over W. So W is the bandwidth. 1 over W will give you the time constant of the baseband, and this is actually giving you some sort of time or time of the carrier. So RC will be much less than the time of the baseband signal, but it will be much greater than the time of the carrier. So it has to lie in between these two extremes. So he has shown these values. So you needed to have RC between 10 to the power minus 10 to the power 6. So you choose it to be 10 to the power minus 5 in the middle. Now, how can we demodulate DSB-SC or double sideband suppressed carrier? So we have seen in suppressed carrier you do not have a carrier. All right. So one thing is that you get the signal and you pass it through a PLL, phase lock loop. You will be also doing them in your subsequent experiments in the lab. So the phase lock loop will actually produce a carrier at the receiver which will have the same phase as the phase of the received signal, received carrier. And hence, your phi will be 0, phase will be 0, and you will be able to demodulate the incoming signal. So this is shown in figure 3.29 here. So phase lock loop will give you the carrier. Carrier goes into the balance modulator. So you will be having terms of the low power at FC frequency, at the baseband frequency. You will just take those frequencies which are at the baseband, and hence you will get M of t. For single sideband signals, again you require phase current reference. And in case of speed signals, you have very small power content at DC frequencies, so you can very well insert a carrier, a very small or a pilot tone, and you can get from the pilot tone you can get the carrier phase, and then you can again multiply it in the balance modulator and then pass it through a low pass filter to get you the signal, as you can see here. Carrier, balance mode, low pass, and you will get your demodulated signal. Here is also saying that for a speed signal you can use figure 3.16. In figure 3.16 you are not using Hilbert transform to generate SSB, rather you were using filters. You were first of all making a double sideband and then you were passing it through a filter so that you just get a single sideband. So you can do that because you have no power content at the DC frequency, so you can apply a filter which even it is not that good, its gain is not that good, still you will get back your upper sideband. Now in vestigial sideband you can send a carrier also for a phase coherent reference. For example, vestigial sideband is used for TV broadcast, so you are sending a large carrier component along with the message signal in the VSB signal, and from the large carrier you can get back the large carrier by passing through the envelope detector, as we saw the envelope detector before. This will also make TV receivers cheaper because of envelope detector requirement. So if you have any questions you can ask. So we have 2 minutes, so we can just study a little bit more. Now signal multiplexing. So we have seen in AM what we are doing. We are shifting the signal from some low pass to some band pass. So in this way, let us say you have 4 or 5 users. You can modulate each user to a different FC. And let us say all of those FCs can be transmitted over channel. So you will be able to multiplex or transmit simultaneously all those signals in a communication channel, where each user is modulated to a different frequency. If we are using double sideband, then it must be that adjacent carriers must be at least 2W away, because that each if double sideband, then each bandwidth is 2W. For other spectrum, and the other carrier must be 2W away, because its upper and the higher frequency lower, they must not clash with one another or must not interfere. This is interference. That is why the distance between them will be equal to 2W. But yes, if you are sending single sideband, the bandwidth will be W, or the difference between your carriers will be W, because you are just sending half of the band. So the various messengers will occupy several frequency bands. They will not interfere with one another, and hence you can multiplex multiple signals over a communication channel. For example, you see nowadays when we are having optical fiber, so they are giving you a bandwidth of 10 MB or 20 EB. For example, in our society, company's optics, so it is giving me a bandwidth of 10 MB or 20 MB. So, and there are various users. So every user is using his signals, and they will be multiplexed to different carriers, and we have a very large bandwidth of optical fiber. So all those signals will be sent through your channel. This is called multiplexing, and you have various methods. One is time division multiplexing, another is frequency division multiplexing. So, alright, the time is up. If you still have any questions, you can ask before I take your attendance. So I've downloaded the attendance.